Okay, so let us get started. So in last Monday, we looked at this problem. Uh, Medusa snakes, and we were looking at divide and conquer algorithms and trying to figure out how this problem related to the earlier problems we talked about, namely the classical binary search as a guessing game between 1 and 1000, and the merge sort, which we also covered. So what I'm going to do today is I'm going to do one more problem on divide and conquer and also uh, implement the algorithm for this problem. So let's get started. So we might recall that we were looking at this problem and we knew that a snake's venom level was X if its DNA had exactly 5X letters, began with X copies of the letter S, then X copies of the letter N, X copies of the letter A, X copies of the letter K, and then X copies of the letter E. So, for example, we had, for example, SS, NN, AA, KK, and EE that would have venom level 2. And what we wanted to find out was, given some string, we wanted to see if by deleting 0 or more letters from that string, we could form a snake of some venom level, and we wanted to know what the maximum venom level was. Now, our first insight into this problem was that it's very difficult to a priori figure out what the answer is. I mean, it's very difficult to, in just one pass through the string, understand whether the snake has maximum level 5 or 6, or it's very difficult to tell. But for example, for this, well, you could say, okay, we have 4 S's and then we have 3 N's and so forth, so it must be like kind of bounded by 3. But if the letters are all jumbled up, it's a little bit harder. But it turns out that the question is a lot easier if you assume you already know the answer and you want to check it. Okay, this is a technique or a strategy that's very prevalent in programming competitions. So let me go to my webcam. So insight 1, right? Assume that we already know the answer. So assume that we think, or we make a guess that the string has some venom level, say let's say level 3. Okay, how do we check it? Okay, we can check it quite easily. So the check itself is actually not too difficult. The check is to look for 3 instances of S followed by 3 instances of N, followed by 3 instances of A, and so on until we get to 3 instances of E. Right? And if this exists in that particular order, then the snake has venom level 3. All right? But we don't know whether 3 is the maximum or not. Our second insight, as you can see over here, is that if the DNA or the string has venom level L, it has venom level L-1, also venom level L-2, up to 1, right? So for example, we looked at this example where we had a snake of venom level 3, and if we knew that the snake has venom level 3, we also know as a consequence that it has venom level 2, simply because we can delete 1S, 1N, 1A, 1K, and 1E from that string. And we would still have a snake of venom level 2. right? So for example, we know, and by consequence, right? So let me kind of try and illustrate this a little bit further, right? So if level L implies level less than L, then, right, level L, or not level L, right, if it's not level L, then it certainly isn't larger. Not larger than L. Does that make sense? I hope that makes sense. So if we know that we have a level L, like level 3, then we know that level 2 is also there. But if we know that we can't make a level 3 snake, then we certainly can't make a level 4 snake because every level 4 venom, I'm sorry, because every level 4 venom must contain a level 3 venom. I'll actually just write this reasoning out. So, for example, right? If we had, we know that every level 4 venom string contains a level 3 venom string, right? So if the snake or the string does not have venom level 3, it can't have venom level bigger than 3, right? Because every level 4, level 5, etc. venom will contain a venom level of 3, or a snake or a string with venom level 3, right? So this leads us to this idea, right? We guess the venom level. This is our strategy. We guess the venom level exactly like we guess the numbers in the guessing game. We notice that these sorts of properties, right? If you like the properties being that in the guessing game, if you know that something is lower than 500, it's lower than anything larger than 500. In the same way, in this particular example with the venom levels, if you know that we don't have a string of venom level L, we know it cannot be larger than L. So we can kind of notice that there are commonalities in the properties. There are commonalities in the properties between the guessing game and this particular problem with the snakes of different venom levels. And that leads to our algorithm. So the idea is we guess the venom levels exactly like the guessing the numbers in the guessing game. And we have a lower and an upper bound just like the guessing game. So the idea is, let's say our our lower bound our lower bound is 0, right? And our upper bound, because we know that the string could just have no s's, n's, k's, a's, k's, or e's, so our lower bound is just 0. And our upper bound is the floor of the length divided by 5. And we kind of explained this. We explained this last week, but I want to go over it again. So the idea is that what is the string, right? The idea is that, let's say I have a level 2 snake. Level 2 snake. Or level 2 venom. Okay, I'm getting my terminology mixed up. The smallest string that has that particular level 2 venom is just S, S, N, N, A, A, K, K, E, E. Okay? And it has exactly, its length is 10. Alright? Now let's say we took the opposite scenario. So I had a length of 10, right? I had a length of 10. Mm-hmm. The maximum string, or the string of maximum venom level, the string of maximum venom level is S S N N A A K K E E, which has venom level 2. Now, what if I had 11 letters to play with? All right. If you had 11 letters to play with, this would still be the maximum venom level we could create. Because in order to create a snake of venom level 3, you need at least the following letters: S, 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 N, 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 A, 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 K, 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 E, E, E. Make sense? We need all of these letters at the very least to create a snake of venom level 3, or a string of venom level 3, right? But we only needed 10 letters to do level 2. So that's where this formula comes from, the floor of the length divided by 5. And in this case, the floor means the number rounded down to the nearest integer. So for example, 11, the floor of 11 divided by 5 is simply, 11 divided by 5 is a 2 and a little bit, and 2 and a little bit rounds down to 2. So that's why the floor of 11 divided by 5 is 2. Make sense? Okay, let's move on. So this allows us to devise an algorithm. So our algorithm is as follows, right? So what we do is we have our lower bound is going to be 0. Our upper bound is length divided by 5. I'm just going to put the floor of length divided by 5. And our idea is that we check the middle. So in a similar manner to the binary search, so while low is less than high, mid is low plus high divided by 2, right? And now we will check if we can make that venom level. So can we make venom level mid? Right? And that means, can we find mid times S, and then mid times N, and so forth, up to mid times E. By mid times E, I just mean mid instances of the letter E, right? Can we find all of these things in the string? Right? And if yes, what are we going to do? Well, we should move the low all the way up, right? So it's just like our guessing game. So if our number was bigger than 500, we moved our low counter from 1 up to 501, right? Or 500. Does that make sense? Because we knew the number is not in 1 to 500, because the number was higher than 500, so we're only searching half the search space. In a similar manner, what happens is that in this case we should make low equal mid, right? And that's because we know we can make venom level up to and including mid, right? But we don't know if we can make venom level mid plus one and so forth. So the space we are searching, the space we are searching for the max venom level becomes mid up to high, right? And what happens if we can't? If we can't make venom level mid, then the maximum venom level, the max venom level must be in low to mid minus one. Low to mid minus one. And we notice that low is just zero. So it's going to be between 0 and mid minus 1. And by doing this procedure multiple times, and by halving the search space each time, we can do this search procedure very quickly. So what does the runtime of this algorithm look like? So let's investigate that. So how do we check, let's say n is the length of the string. So how do we check whether a string has venom level mid, right? Well, what we have to do is we have to go through the entire string, checking for 5 instances of s, followed by 5 instances of n, followed by, mid instances of s, mid instances of n, mid instances of a, and so forth until we get to mid instances of the letter e. All right, and this will take O of n time for checking if we can make venom level mid. Okay? But what about the binary search that we're doing? Well, that's a little bit different, right? So how does that work? Well, it turns out that we know that binary search itself takes O of log n time, right? So binary search by itself takes O of log n time. But inside the binary search, in order to decide whether we should move our low counter up or our high counter downwards, we have to do O(n) work inside to check that. So it turns out that we have O of n work to do inside a procedure that takes O of log n time. So the overall running time is O of n times log n. Right, and you might notice that this is actually similar to the merge sort. Recall that in the merge sort, what was happening was we were doing kind of a binary search-like procedure where we were dividing the search space into halves, and then the combining step was the merge, right? And merging everything together took linear time because we had to go through the two sublists and merge them all together. So does that? I hope that makes some sense. And now we are going to implement it. So let's do that. Let's get up our Python terminal. Hopefully this should work. Okay, let's make a new window. All right, hopefully everyone can see my terminal window. So let's get started on the implementation. So the first thing we're going to do is create a procedure that will be able to check the venom levels. So let's do that. Okay, so let's define a function called check level. And what it's going to take is a string, let's call it st, and a level. Let's call that level. Okay, and what it's going to do is it's going to check if the string contains the level instances of s and then level instances of n and so forth. So we can make a string of venom level inside that string. Okay, so what we'll do is let's define s count, n count, a count, k count, e count, and let's make them all 0. 0, 0, 0, 0, 0. And what we're going to do is now we're going to loop through the string. So for I in range len st, so we're going through the string. So now what we're going to do is we're going to check if we have level instances of s first, right? So if s count is less than level, right? Then what? If the ith index, right? If the character at index I in our string is an s, add 1, right? S count plus equals 1. Okay, and what happens if we have reached that number? If we've reached, say, if we're, say, looking for level 3, if we've reached 3 s's, we should now look for n's in the remainder of the string. So what we're going to do is we're going to do exactly the same thing. N count is less than level if st I and n count plus equals 1, and same with a, k, and e. A count is less than level if st I is a count plus equals 1, l if k count. And now we're just going to check at the end if we manage to get more than level instances of the particular of all of the characters. So a simple check is, I'm sure there's a more efficient way to implement this, but I'm just doing this off the top of my head. So if s count is bigger than or equal to level, and n count is bigger than or equal to level, and a count is bigger than or equal to level, and k count is bigger than or equal to level, and e count is bigger than or equal to level, okay, then, well, we answered our question, right? Then we answered the question, meaning that we can make a string of venom level right? So we should return 1, meaning yes, else return 0. So I'm just going to write return 0 here. Okay, the next part of our plan, is to write the binary search. So let's do that. Okay, so define binary search, and it'll take in a low, a high, and the string st. So while low is less than high minus 1, I mean the particular condition for when this is terminating really depends on the exact type of thing you're searching for. The reason why it's high minus 1 and not high is simply because, well, if you find a snake with venom level L, then that is kind of included in your maximum calculation, whereas L plus 1 is not. So little things like this make a difference. But yeah, when you go and implement this, you should really you should really think about why the condition works like this, or maybe you can change the condition and change the way the function works, and it'll still work the same. So yeah, the important thing is just to, it's one of these sorts of permutations of this sort of function. The overarching idea is exactly the same, it's just the little details that might be slightly different. So okay, mid equals low plus high divided by 2, and we're taking the floor of that. So if check level st mid, right, because we want to check if we can make a venom level mid from our string st, then what are we going to do? Well, we're going to set low equals mid, right, and otherwise we will set high equals mid minus 1. And as a last check, in case we have like 2 integers to choose from, we'll just do a condition for that. If check level st high is 1, then I think we should return high, right? Why is that? Because we just want to be sure that in this case, this will terminate when low and high are exactly separated by 1. So if they are separated by 1, we only have 2 options to choose from. So if we can make high, then we pick it. Otherwise, we pick low. So else pick low. Return low. And we're basically done. So now all we have to do is do the define our upper and lower bounds and do our file input and output, and we will be finished with this implementation. So let's do that. Input file is open. Snakein. I'm pretty sure this is the file we've got to read from. Snakein.txt. Output file. Open snakeout.txt for writing. And we find the length of the string. Input file, line. And we get the string in. String. Let's do input file dot read line dot strip, right? I mean, there might be a couple of bugs in this code, but yeah. This is the basic idea. And now we will say answer is the binary search of where the low is 0, the high is length divided by 5, rounded down to the nearest integer, and we have the string as an argument. And now we simply do output file dot write answer. Oh yeah, let's make that a string, and we close the files. Input file dot close, output file dot close, and we're done. So what we have here is we have a check level function, which essentially verifies if our guess is okay, and we have a binary search as the guessing scheme. So we guess and we try and halve the search space each time, depending on if we get the answer right or not. And we want to find the maximum answer we can get. So if our answer is good, it means that we might be able to do better, so we can halve the search space. And if our answer is bad, it also means we can halve the search space because it can't be any higher than what we got. Okay, so let's move on to a tougher example. Okay. Now you might remember this problem from the workshop on brute force algorithms. And if you don't, then, well, I encourage you to go back and kind of watch the few minutes of explanation on how this problem works and what you have to do. Yeah, just go back and watch it if you have some time. So what we found earlier on this problem, if you remember, what we had to do was that we have this pyramid, we have some number called the base, and we add these, and the rule is to get to the next row of the pyramid, you add the two numbers, add the two numbers in the bottom row that are vertical from that particular number, and then you subtract to the base. In this case, with b equals 100. So for example, in this case, 61 plus 88 is 149, and then you minus the 100 to make 49. And for the top row, you just multiply the numbers together. And the idea is you're given some number of integers, from 6 to 32 integers, and you want to make the largest number at the top of the box that you possibly can. Now, we tackled this problem with brute force earlier. We said, okay, find all of the ways to choose the 6 numbers at the bottom from the 32 possible choices. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. We have 8 choices here. And we said, find all ways to choose 6 numbers from 8 numbers and permute them. Try all possible permutations for the bottom row. See what you get in the top row, and choose the biggest thing. Now, what we realized was this is not a particularly efficient algorithm because this runs in s to the 6th time, right? So we know that the number of ways to permute 6 elements from s elements is s permute 6, which is s factorial divided by s minus 6 factorial. And s factorial divided by s minus 6 factorial is s times s minus 1 times s minus 2 times s minus 3 times s minus 4 times s minus 5. Okay? And there are 6 expressions there, and each of them contains s. So approximately, the running time is proportional to the 6th power of s. So s to the power of 6. Now, for s equals 32, 32 to the power of 6 is a big number, and it is bigger than the number of operations a computer can do in 1 second, which is approximately 50 million. Okay? So brute force would do okay. It could solve small inputs, but it wouldn't be able to run fast enough to score full marks. So how might we go about doing that? The idea, and I told you that this would be quite a difficult problem, but the idea is to use binary search. Okay, so this is not an easy concept. This is a pretty difficult application of binary search, but we're going to study it anyway. So I've kind of graded the examples in terms of difficulty, right? The classical guessing game was easy. Merge sort was kind of medium. Pretty hard to like maybe figuring it out would have been somewhat tough. But once you understand the idea, it's very simple once seen. Okay. The Medusa snake example is similarly kind of a little bit tougher, right? But once you have the insight that it's very hard to find the solution in one pass through the string, but it's easier if you know the answer, if you can guess the answer. It's very easy to verify that you can make a certain venom level, right? That's the key insight into that problem. And once you know that, then the binary search algorithm already suggests itself. But this one is kind of hard, okay? So the key insight is almost comical, and there are several, after you get that key insight, there are several other things you have to do, like implementation details and everything, to get this problem correct. So it's not particularly easy to implement, and I won't be implementing it today, certainly not. But I have implemented it, but I will not be doing it today. And yeah, there are several like finicky details, but we're going to neglect the finicky details for now, and in terms of implementation, and just talk a little bit about the idea and the insights, because that's really what's important in programming competitions. Ideas and insight. So let's go back to our notes. Okay, let's get on with it. So, my camera needs a little fixing. Okay, that's good enough. So stacking numbers. All right. So the key insight for this algorithm is quite unintuitive, but once you understand where it comes from, it'll become intuitive. So the key insight. Let's talk about the key insight. So the first thing is, you probably will not find this insight unless you have already understood the brute force algorithm. Sorry about this. There we go, that's better. Yep, there we go, my camera is all fixed. Yeah, so you'll probably not understand this key insight until you know about the brute force. So the key insight is, first of all, brute force takes OS the sixth time, which is not fast enough for s equals 32. But I've already told you that, right? So what am I saying? Why is this key? The idea is that imagine our algorithm. Imagine our algorithm took O of s to the 5 time instead of O of s to the 6 time. Okay? Imagine we could somehow get rid of one order of magnitude, right? So we could somehow reduce the polynomial so it was not s to the 6, but it was s to the 5. Would it be fast enough then? And the idea is we will be fast enough. So we don't require some sort of other mathematical method for doing this, right? For generating the number at the top. What we require is some way of chopping our running time even by one order of magnitude, and that will be enough. That's the key insight to this. And it just comes from just being a bit curious, like what sorts of algorithms you can kind of you can work backwards from the running time to the algorithm and say, okay, if O of s to the 6 is not going to score full marks, then does O s to the 5 score full marks? What about s to the 4? And it turns out s to the 5 will make it, but s to the 6 will not. Now, what do we know has a running time of O of s to the 5? Well, permuting 6 elements has a running time of O of s to the 6 times, so permuting 5 elements has a running time of O of s to the 5 time. So this is the second part of this insight, right? Permuting 5 elements from S elements has running time O of s to the 5. So that suggests something, right? Could we somehow generate permutations of 5 of the numbers and then find the 6th number in some other way? So, assume we permuted 5 numbers. Okay? From the set of S. Okay? S numbers. Could we find the 6th number that gives us the maximum score at the top? Okay, so now in order to do this, let's recall the following idea. We said earlier that the number at the top row is given by, let's call it P times T, where P is equal to A plus 4B plus 6C plus 4D plus E mod base, and T is B plus 4C plus 6D plus 4E plus F mod base. If you don't know where that comes from, look at the last workshop on brute force, because we worked through this. Okay, so now we know that each element is less than the base. So we know that, assume we permute A, B, C, D, and E. So let me write this on another page. assume we permute A, B, C, D, E. Okay? We know that since all numbers are less than or equal to the base, since all numbers are less than or equal to the base, that f is less than or equal to the base. So we can simplify this as a plus, so we know this sum, a plus 4b, oh sorry, I'll say this again. So we know that t equals b plus 4c plus 6d plus 4e plus f mod base. By mod base, I mean like you take the remainder when you divide by base, which is the same thing as just subtracting it off in this case, because all the numbers are less than the base. This is the same thing as saying b plus 4c plus 6d plus 4e mod base plus f. Okay? Because f is always less than the base, right? There's this rule that if you have like two numbers, like a and b, and you mod them by some number, then it's like a mod that number plus b mod that number, and then you mod that number again. So there's this rule which is like alpha plus beta mod n is alpha mod n plus beta mod n mod n. Right? I hope that makes sense. So in the same way, t, which is like this whole thing mod base, is just this mod base plus this mod base, right? So yeah, and what we want is that we want this thing to be as close or as close to the base as we can. Okay? I hope that makes some sense. So once we compute b plus 4c plus 6d plus 4e mod base, right? We need to select f to be the largest element in the array of s elements that we have left that is less than the base. Okay? Yeah. So what we need is for t and s to be as large, as close as possible to the base, right? So let me try and explain this another way. So we want t needs to be close to the base, right? Because we want s times t to be large, so we need s and t to both be as close to the base as we possibly can make them, right? We know that we have reached a certain number with b, c, d, and e. So we need to select the f. We need to select the f so that it's less than a certain number, right? We need f, right? We need that b plus 4c plus 6d plus 4e mod base, right? Plus f to be as close as possible to the base. Which means f has to be the smallest number the largest number, or the largest element less than or equal to base minus B plus 4C plus 6D plus 4E mod base. Okay. Now, how do we find the largest element that is smaller than some number in a list, right? I mean, one way is just to search the list, but another way is simply to sort the list first and then do a binary search over that list. So this is like insight 2 already. In fact, I think this is like insight 3. There's a lot we need here. But the point is that now we can do a binary search for the largest element that is less than some number in a list. Okay? And it turns out that's very similar to just finding an element in a list. And therefore, we only need to brute force 5 permutations of 5 elements. And in fact, you can see that we could have also done the same thing with S and with element A instead of F. So it turns out because the pyramid is symmetrical, we only need to permute 4 elements instead of 6. So in fact, our algorithm, or our algorithm that will work and score full marks, has a time complexity of O of S to the 4 times log S. So let me write that down. O of S to the 4 times O of S to the 4 log S. And that is the running time of an algorithm that will score full marks. So I'll leave it as an exercise to you to kind of implement this and go through all of the details and really try and understand how this works. But yeah, this is a particularly difficult binary search problem. This would be a very hard binary search problem in a programming contest. But yeah, thanks everyone, and see you next Monday, which I think will probably be the last session for the semester. Thank you.